Welcome back to the lecture series on optics and spectroscopy. In this lecture, we are going to discuss three topics. 1. The concept of Newton's rings. Second, we are going to discuss an experimental procedure to calculate the wavelength of a monochromatic light source using the concept of Newton's rings. And third topic, we are going to discuss about the interferometer, an interferometer which is used to calculate the refractive index of a given gas at a given pressure. That method is called Jamin's interferometer experiment. These three topics that we are going to discuss in this lecture. Newton's rings. The concept of Newton's rings. We will consider a setup where we have one plane mirror in which a convex lens is placed over it, right? A convex lens is placed over it. Assume this setup, right? It's like this is a plane mirror, and this is the lens. So it is plane mirror and this is convex lens, and the radius of curvature of this lens is this is the radius, and again this is also the radius, right? Let us assume a situation like this. A convex lens is placed right over a plane mirror. Here we can notice that this convex surface which is in contact with the plane mirror. So this is the three-dimensional diagram. If you look into it, so we can draw it in a two-dimensional diagram. So this is the plane mirror and it is convex lens. Okay, so the surface of the convex part is in touch with the plane mirror, let's say PQ. So this plane mirror PQ and the convex lens, let's say AB, the surface of this AB is in touch with the point O. Let's say this is origin. So at point O, right, from point O, if we move forwards, here it creates an air film, right? There is an air gap, it creates an air film. So the thickness of the air film at the point where these two materials met is 0, and it gradually increases. It gradually, see, so this side it is flat and here it is gradually increases, so that this thickness of the film, this air film, slowly increases, right? Now, if a monochromatic light is allowed to pass through it, likewise, what will happen? This monochromatic light, let's say S, which will be getting reflected from the surface, the bottom surface of the convex lens, that is this convex surface, it will be getting reflected from convex surface, and also for the incoming light ray, it is partially reflected in this surface and it is partially refracted into this air film, and it getting again reflected at this plane surface, plane mirror, so that again we have one another reflection from this point, right? Now we can say that this is ray 1, this is ray 2, these both are reflected rays. Okay, reflected rays. These reflected rays undergo interference. So these reflected rays undergo interference, and it forms due to the interference, it forms a concentric bright and dark circles or bright and dark fringes like this. Wherever there exists a constructive interference, there the bright fringe occurs, and wherever there exists a destructive interference, dark fringes occurs. All these circles have common center. So these fringes are called Newton's rings. Earlier in the previous lecture, we have seen a case where we have a variable thickness air film. There we obtain straight line fringes, bright and dark straight line fringes, and we have calculated the fringe width in that lecture. Here this one part of this wedge is increasing, it has a curvature, so that we are having, and this is, see, this is a three-dimensional material. So see, we have a situation like this, that is the thickness about the radius, the thickness of the air film, the thickness of the air film is same about the radius, right? If this is about the center, if this is the center for a particular radius, so we have a circle, all this particular radius. So if this is origin, so from origin at a distance r1, the thickness will be same, right? At the thickness r1, the thickness will be same, so that for that particular thickness we have either bright or dark spot, depending upon which condition is to be satisfied. And if you increase the radius and the thickness throughout this radius is also same, here according to which condition is satisfied, we will have a particular a bright or a dark ring, so that we will have a concentric rings, bright and dark rings consecutively. So these rings are called Newton's rings. So Newton's rings is formed when interference occurs when the light ray interacted with the Plano convex system. So it is called Plano convex lens system. So this creates Newton's rings. So this is the idea of Newton's rings. Now see, as the rings are formed, we need to calculate the radius of the rings. We need to calculate the radius of the rings. So that is what the next part of our discussion. So what is the radius of a particular ring from the center? Okay, so radius of the rings, radii of the ring. So radius of the rings. So for this purpose, let us consider a situation. And see, let us draw the Plano convex system like this. So this is plane lens, and let me complete the entire system with the circle, right? This is a portion, a plano convex lens. This is the curvature of it's a curvature. When I extend this curvature, it will create a circle. Let me draw that circle. Let me draw that circle and the plane surface. Now this point is O, and this is P, and this is Q. Let it be, and this is the center. Now let's draw a vertical line. Let's say this capital R is the diameter of this circle, and let us consider the rth ring. So let us consider the mth ring. So the first ring, second ring, third ring, fourth ring, like that. Let us consider the mth ring, right? The mth ring, so which is occurred at somewhere here. So at this point, let's say at this point, this is the thickness of the film for mth ring. So this is the thickness. We can define this thickness is T. So, and you can extend this. So everywhere it is T, so that at this point we can define a point B. And this is O, right? And along the direction of this thickness that we have considered, we can draw a line in the circle. So this line is chord of the circle. This line is chord, and this is diameter. And let us name this as D, this as C, for example. Okay, let us consider. Now this OB, we can write this OB, which is equal to this thickness, and this thickness at this point are same, which is equal to T. Okay, and earlier we said R, that is diameter of the circle. Okay, now, so we said DZ is the chord, and this O, let's say this point as, let's put this point as E. So OE is the diameter. Okay, so from the theory of the circle, from the geometric theory of the circle, we can write the product of the intersection portions of the chord and diameter are same. That is product of intersection points DB and BC. So DB cross BC, which is equal to the product of this intersection point, the diameter side, EB and BO. EB multiplied by BO. Okay, fine. Now this length is what? This length will be the radius of mth ring, right? We said this is the thickness for mth ring. So this is the thickness for mth ring. If this is the case, then this is the radius for the mth ring. So this is the radius for mth ring, that we can define Rm. In that case, this is also equal to Rm. So this side it is dB equal to Rm multiplied by BC is also equal to Rm. What is EB? EO is nothing but R. So that if you want EB, that is R, this is center, and if it is the case, or we can define, instead of R we have defined as diameter, instead let us define this as radius. Okay, let us define this as radius. If R is radius, means from this point to this point it is radius R. Okay, so if you want EB, then it is nothing but, so EO is 2R, okay, EO is 2R. EO equal to 2R if R is the radius. Okay, earlier I said it is diameter. Sorry, let us assume it is a radius. Okay, so in that case, EO is 2R, and what we want? We want EB. So if you want EB, we have to subtract this portion BO from EO. What is BO? BO is nothing but T. So 2R minus T, that is equal to EB. So EB 2R minus T multiplied by BOT. Fine. So this side it is RM square. Generally this is the thickness that is very, very small, right? So when compare with R, thickness will be very, very small, so that you can take R minus T is equal to R, so that 2R minus T also you can consider as 2R, so that 2R multiplied by T, it is RT. Fine. So this you can say equation number 1. Now from our earlier discussion, let us recollect the condition for the dark fringe. The condition for the dark fringe is 2nt cos R, that is equal to m lambda. In our case, right, if the light is made to incident on the Plano convex system perpendicularly, and now then R equal to 0, so that 2nt, so cos R becomes 1, so the 2nt which is equal to m lambda, so that T becomes m lambda by 2n, it is equation number 2. Substitute that expression for T into equation number 1, we will get Rm square, which is equal to 2R multiplied by m lambda by 2n. So this 2 and this 2 will cancel out each other, so we will have m r lambda by n. So the Rm square is equal to m r lambda by n. So if you want Rm, radius of the mth ring, this is equal to square root of m r lambda by n. So this expression is the radius for the mth dark ring. Okay. Now if you want the diameter of that, diameter of the mth dark ring, what you have to do? You have to multiply it by 2. So if you want the diameter of the mth ring, it is nothing but 2 times Rm, which is equal to 2 square root of m r lambda by n, or you can write 4 m r lambda by n square root. So that you can write the expression for the mth dark ring as square root of 4 m r lambda by n. Okay, so this is the expression for the radii of the rings. So it is for radius of the, this expression for radius of the mth dark ring, and this is for radius of diameter of the mth dark ring. Fine. And the next part of this discussion is, using this formula, we are going to discuss an experimental procedure to calculate the wavelength of an monochromatic light source given to us. Determination of wavelength of sodium vapor lamp using the concept of Newton's rings. First, let us draw the experimental setup for the Newton's rings. It's nothing but the one equal to the one that we have discussed in the previous lecture for the calculation of the fringe width with the air wedge. In the place of air wedge, we are going to replace with the Plano convex lens system. So we have so this is the Plano convex lens system. Fine. And this is the eyepiece, or you can say it is, and this is, this is the telescope part actually. It is traveling microscope. The entire system here is traveling microscope. Fine. This is the experimental setup for the determination of wavelength of sodium vapor lamp using Newton's rings. Here, this is the Plano convex lens system. Okay. Now, a light is coming from a light source. This light is nothing but sodium vapor lamp, whose wavelength is going to be calculated using this method. Now, this incoming light ray is converted into plane parallel using this parallel light concentrated, and this light is allowed to getting reflected in a mirror. This mirror has the property that part of the light will be reflected and part of the light will be passed through it. So here the angle of inclination is 45 degree, so that incoming light ray hit this mirror with the angle of 45 degrees, so that angle of reflection also will be 45, that is, and if you draw a normal to the lens, this angle will be 45 degree, and this angle also will be 45 degree, right? So that this incoming light ray, it diverted 90 degree and it travels perpendicular to the Plano convex lens system, right? After getting reflected at 2 points in the convex surface and the plane surface, and it is reflected, and the reflected light ray travels again along the direction of incoming light ray, and it passes through the lens system, and it is observed in the traveling microscope. Due to the interference phenomenon happened in the Plano convex lens system, you could able to observe concentric rings, concentric bright and consecutive bright and dark circles in the traveling microscope when the traveling microscope is adjusted suitably. So that now what we will be observing is, we will be observing the concentrated bright and dark circles. So after observing this, we need to do the experiment. From that experiment, we have to calculate the like this. So we are going to do the experiment. From that experiment, we are going to calculate the diameter of the mth ring, diameter of the nth ring, diameter of the pth ring, right? So this is 0. See, if you calculate the diameter of this ring, it is the diameter of the first ring, right? But when you look into the when you look through the traveling microscope, there are a large number of concentric circles which are closely packed, not as like that we have drawn in this picture. You could see that all the rings are very close. So we would have experienced only very small distance between bright and dark rings, so that it is very the rings are closely packed, right? Now what we have to do is, we have to spot the center, right? We have to spot the center. We have to put the crosswire at the center. Then, right? Then slowly we have to move the traveling microscope center to right side, right? Center to, if we moving it, the first is, what is that? First is first ring, second ring, third ring, fourth ring, right? So we can say that this is fourth ring and this is fifth ring. So we can fix the cross wire at the fifth ring, fifth dark ring, you can say. Then you can fix the cross wire on the fifth dark ring. Then you can take the reading, main scale reading, vernier scale reading, total reading in the horizontal scale of traveling microscope. You have noted down. Then again you can move this for another fifth. So this 6, 7, 8, 9, 10. Let's move to the 10th ring. We have to note the reading. So in terms of every 5 rings, we have to take the traveling microscope's horizontal readings. We have to put it in the table. Then again, so after taking 5, 6 readings, come back to the center again, then move to the left. Again you calculate the reading for the 5th ring, 10th ring, 15th ring. So putting the crosswire on 5th ring, 10th ring, 15th ring and so on, we have to note the main scale reading, vernier scale reading, total reading in the horizontal scale of the traveling microscope, right? So from these readings we can able to calculate the diameters, and from the diameter we can able to obtain the wavelength. So that we will explain just after drawing this reading table. Okay, rings experiment, what we have to do first, as I said, we are moving the crosswire in the forward direction, in the right direction, right side direction from the center. So we are placing it in the 5th dark circle. So, and we are measuring the horizontal reading, right? So number of ring, 5th ring, and we are writing the main scale reading, vernier scale reading, total reading. Let's say this is TR1, total reading on right side 1. Then what we are doing, we are moving for another 5 lines. So it is 10th ring. Again we are noting the reading, it is TR2. Then again for 15 we are taking main scale, vernier scale, and we are writing TR3. So likewise, so for 10th reading we will have the 50th circle, so it will be TR10. okay, so these all we are taking the readings of the horizontal scale of traveling microscope by moving the crosswire in the right direction. After completing the 10 readings, you again come back to the center. You do the same for left movement. So now, okay, so let's this right movement, and this is left movement. Okay, so if you are doing it on left side, again you will get here it is left side reading 1, left side reading 2, left side reading 3, right? And we are getting TL10, right? So it's like, you see we are having, so if this is the 5th, assume that if this is the 5th, then in the right side we are having TR5. So this, for the 5th ring we are having TR1, so this is the TR1. On right side, in left side TL1, right, the 5th ring. So the distance between this, when you take the difference between TR1 and TL1, that is nothing but the diameter of the 5th ring, diameter of the 5th ring, so that we can subtract one from other. So right, we can subtract the bigger number from the smaller number when comparing to these two, and we are getting diameter. So this diameter will be D5. This the diameter of the 10th ring, and this is the diameter of the 15th ring, and so on. We will get the diameter of the 50th ring. Okay, fine. Now here, if you square it, you will have diameter square of the 5th ring, diameter square of the 10th ring, diameter square of the 15th ring, diameter square of the 50th ring, that is D square. Now what we need is, let us subtract this D10 square from, no, subtract D5 square from D10 square. What we will get, see what we are doing, D10 square minus DP5 square, okay, the difference we will get. And similarly here you can write dm square minus dp square. So the difference, let's have the difference always m minus p, which is equal to 5. If you want to keep this m minus p which is equal to 5, then you have to subtract this value from this, this value from this, this value from this, and so on like this. So you will get 9 readings. Let's take the average. Let's take the average of dm square minus dp square. That will give you the difference in the diameter of the 5 rings. This readings will give you the difference in the diameter of 5 rings. That is, it will give you, the first difference will give you the diameter, the difference in the diameter of 5th and 10th ring, and the second reading will give you difference in the diameter of 10th and 15th ring, and third reading will give you the difference in the diameter of 15th and 10th ring, and so on. So if you take the average, you will get the average differences of the diameters of 5 rings. Okay, good. Now we are having dm square minus dp square formula. Okay, that is fine. See, we have the equation for diameter of the dark fringe, which is nothing but, so diameter of the dark fringe, which is nothing but mth dark fringe is 4 mr lambda by n, right? And so this is the equation that we have derived just earlier in this lecture. Now if we rewrite this for dm square, you can write 4 mr lambda by n, 4 mr lambda by n, right? You can also rewrite, this is for the diameter of the mth ring, and if you want to write the diameter of the pth ring, then you can write 4 pr lambda by n. Okay, so here this is air film. The refractive index of the air is equal to 1, so n equal to 1. Now if you write dm square minus dp square, you will get 4m r lambda, n becomes 1, so 4m r lambda minus, here also 4p r lambda by n equal to 1, so 4p r lambda. We can take m minus p, so 4r lambda is common, 4r lambda. Okay, here in this case let's put mps 5, right? And you know what we need is, here this is dm square minus dp square. What we need to calculate is, we need to calculate the wavelength. So we have to rewrite this equation for lambda, so that lambda, which is equal to dm square minus dp square divided by m minus p 4r. See, this is the equation to calculate the wavelength of the sodium vapor lamp used for this experiment. But see, here dm square minus dp square that we have obtained from this equation, obtained from this tabulation. So this is okay, we have, and we have defined m minus p, which is equal to 5 in our example case. So this is also defined, 4 is constant. If you could able to calculate, if you are knowing the radius of this convex lens of the Plano convex system, then we can able to calculate the lambda. So this radius r can be calculated using Boy's method. Okay, so that will be the another topic of discussion, which we are not going to discuss now, but r can be calculated using Boy's method, provided assume that r is given. So now we can able to calculate the lambda using this procedure just we have explained. So this is the method of determination of wavelength of sodium vapor lamp using Newton's rings. And next point, we are going to discuss another topic, Jamin's interferometer, and which is used to calculate the refractive index of a gas material. Interferometer, it is used to calculate the refractive index of a gas material. In this topic, let me draw the diagram first, and we will discuss the theory in detail. So this is the experimental setup. So it is the experimental setup for the Jamin's interferometer. Let me explain a bit about it. So there are two lens systems, plane lenses. It's a thin lenses A and B, right? Here in the lens, the top surface will have partial reflection and partial refraction, and the bottom surface is completely polished on back side. So whatever the light comes into it will be completely reflected. So this is the property of this system. There are two lenses, and then here there are two tubes. These tubes are allowed to pass the light through it in its horizontal direction. And here there is an C1, C2. It is calibrator. There is a calibrator setup. It is a glass plates of equal thickness, right? Glass plates of equal thickness, and so this is observer. It is microscope, and the light source S is placed here, and this light source is made as parallel light using this light concentrated here. Okay, so what happens is a light is coming from the light source S and it is become parallel at this point. This parallel light source is allowed to getting reflected at the lens A. Here two light rays are created. One light ray that is a direct reflected light from the upper surface. Another one is the light ray reflected from the lower surface. So that because it is travel into the lens and getting refracted back, so that there will be a path difference created between ray 1 and ray 2. This ray 1 is allowed to pass through the tube 1, ray 2 is allowed to pass through the tube 2, and both are again allowed to getting reflected again in the lens system. So here the ray 1 is getting reflected in the inner part of the glass plate. It is mirror, not lens. These two are mirror systems, so that it is in the inner part of the mirror, while the ray 2 is reflected back in the outer surface. So thus both will getting interfered at this point, and it is getting here. And the uninterfered after the interference, the resultant light ray is getting in this telescope. Okay, and roll off this portion we will explain little later, and this diagram is related to this calibrator. Now what happens is, if there is no gas is filled, if the tube is empty, then what happens, this light ray is getting interfered and we are getting a dark spot, right? We could be able to get a dark spot, and dark fringe we can observe, and we will focus the crosswire of the microscope in the dark fringe. Now if we allow a gas into one tube, what happens is due to the when you slowly fill the gas, when the gas has some refractive index, and this when the pressure is increased, what happens here, from the dark spot there exists a bright and dark spots because of the path difference created due to the pressure change of the gas, so that we can able to observe the movement of that fringes in one direction in the traveling microscope. We need to measure the number of fringes crossed when applying the gas pressure, and from that number of fringes crossed from dark spot we could able to calculate the refractive index. But the thing is, these fringes will be moving very quickly, so it is very difficult to count the fringes in fringes when it is on when the gas is filled. So that we are creating a calibrator. So this setup, these two are the glass plates, and it is connected to connected to a circular disc D, right? So that there are two markers. One is from C, another one is from C2, right? If you are moving this glass plate in one direction, then the path difference will increase. The net path difference between these two rays will increase. If you move the glass plate in another direction, then the path difference will decrease. Now we will choose the direction where the path difference will decrease, so that after filling the gas, so we have there are some n number of fringes will be crossed. Now what we have to do is, we have to move this, we have to adjust this one of the glass plates, either C1 or C2. By adjusting that, these fringes again moving in the reverse direction. While it is moving in the reverse direction, we could be able to count, because we are doing it slowly and we can count. So count until again the dark fringe is observed, so that we can able to get the number of fringes that is passed through this telescope when the gas is filled. Okay, so this is the idea. Now this disc is, its reading is mentioned in terms of refractive index, in terms of number of fringes, fringe shift and refractive index. So from this disc we could be able to directly write the refractive index of the gas material. Let me write the equation for that. So let N is the refractive index of the gas. N is the refractive index of the gas. Then L is the length of this tube. L is the length of the tube. L is the length of the tubes. Both tubes have same lengths. same length, so that length of T1 and T2. So now path difference between the rays, two rays, is n minus 1 times L. Okay, for n minus 1 times L, right? Now for the bright fringe, we can write n minus 1 into L, which is equal to m lambda. Okay, and if you are knowing n, L and lambda, n, L and if you are knowing the L, m and n, m is the mth fringe, lambda is the wavelength of the light source, L is the length of the tube. If we know these parameters, then we can able to write the refractive index. How to do that? You can rewrite this equation, n minus 1, which is equal to m lambda by L. So n minus 1 equal to m lambda by L, n equal to m lambda by L plus 1. So this is the simple equation for the refractive index. Okay, the thing is, we need to calculate the fringe count, right? If we fill the gas, we need to calculate the fringe count. What is that? The simple statement is, without gas, we can focus the telescope to the bright central spot. Then if you allow the gas, the bright and dark spots, so that fringes will be, bright and dark spots will be appeared, and the fringes will be moving in one direction. But as the fringes are quickly moving, we couldn't able to measure the numbers, so that the calibrator comes into the picture, right? And this calibrator, there are two equal thickness glass plates are there. If you rotate the glass plate, the path difference either be increased or be decreased depending upon the rotation of the shift. By rotating it in the reverse direction, we could able to count the number of fringes, so that using that number of fringes, we can put the m value, lambda and L values are known. Substituting it, we will get the Jamins interferometer. Now we will get the refractive index of the gas material using Jamins interferometer. One point is that and there is a disc which is a circular scale. This scale itself give you the direct value of refractive index of the gas material, that is the m and the refractive index, right? As this is a material, this material, this is an experimental setup. For this experiment, what is the light source used and what is the length of the tube, that is predefined, so that lambda and L is predefined, so that if you could able to count the m, then the scale will automatically tell you what is the value of n, right? That is the idea. So this is a simple experimental setup for calculating refractive index of the gas material. It is named as Jamins interferometer. Okay, we have just discussed the outline of this system. Here these two are the mirrors. These two are the mirrors. It is like a thin film. It's like it will act like a thin film, right? In this, the upper surface will have a partial reflection, partial refraction, while the lower surface is completely polished, so that it will only have complete reflection. So this is the idea. So with that, let me stop this lecture, and we will resume back in the next lecture. We will start to discuss about the concepts of diffraction. Thank you for watching, and if you have any doubts or any clarifications required, and you can ask in the comment box, and I'm being there to explain them in a clear manner in the comment box itself. Thank you very much.